Thank you very much. So this presentation will be a bit different from what we have seen during the conference, because I will not speak about some formulas, some results, or something else. I want to draw a connection between the problems we treat in MATH.en.JEANS and later on in research. It's the same thing, essentially. And why we do them and why it's interesting to work on them. And so before I start, I want you to know that I'd like you to ask questions immediately when you have them, not wait until the end. When there's a problem, you don't understand something, raise your hand, ask the question, and perhaps even if in the chat there's a major question, we can answer it directly. It's better for the understanding. Donc du coup, si vous avez des questions, n'hésitez pas à la poser directement. S'il y a un problème, vous ne comprenez pas un truc. Et vous pouvez poser en français. Moi, je vais faire la présentation en anglais pour que tout le monde comprenne. Et voilà. Okay, so let's start. The presentation is called Drunkards and Mathematics. So I'll have to speak about alcohol problems. And the idea is the following. We've got a rather well-known problem, or perhaps some of you have already seen it somewhere. It's called the Drunkards problem, where we've got a mathematician. She worked hard all day long and had some difficult proofs, and in the evening she goes in a bar, drinks a bit of beer with her friends, and then when the bar closes at 5 a.m. in the morning, she leaves, and she has to find her way home in the street. Okay, she lives in the same street. The street is very long, but she is in the same street, and now she has to decide where does she live, and she completely forgot. She had too much beer, so what she does is say, okay, let's just choose randomly. I've got a 50-50 chance that I got the right direction. So perhaps she goes right at the first step, and then she looks at the house, says, oh no, that's not my home, takes a sip of the beer she still got, and completely forgot from where she came. So she has to decide again, where do I go? Takes a 50-50 chance, right or left. Perhaps she goes again to the right, looks at the house, sees that it isn't her home, so she forgot where she came from and has to decide again. And perhaps this time she goes to the left, and then the next step perhaps to the right, okay? And now the question is it possible for her to go home, or is there a chance that she gets lost in the street, goes completely off to the wrong direction? Okay, so we've seen similar problems yesterday with the presentation from Lucie Lyon. And so as I said, I'm not going to answer. Okay, that's your problem. Perhaps next MATH.en.JEANS, I don't know. That is not my presentation. I want to know why we're interested in this question. Okay, and I mean, at first glance, it's very nice. I mean, it's very easy to present. I hope it was clear in the 5 minutes that I took to present the problem. On the other hand, it's very hard to study. Okay, so if some of you have already tried to answer parts of this question or related questions, then you probably have seen that it's not easy to get an answer directly, and you have to work hard to get something. And the third nice thing is it has a link with reality. I mean, we speak about drunk people. Yes.
Dans l'image qu'il y avait juste avant, les maisons, est-ce qu'il y avait des maisons, c'était pas, je crois qu'il y en avait 6, c'est ça? Est-ce que la 6e à droite, c'est la dernière maison ou il y en a après?
Non, ça va continuer. Okay.
Parce que s'il y a une limite, bah, la personne, comme elle ne peut plus aller à droite, elle est obligée de retourner à gauche. Mais s'il n'y a pas de limite, c'est plus.
C'est juste un schéma, donc il y a une infinité de maisons à droite et à gauche. Okay. Okay, and now, because we have links to reality, everybody is happy. Because even though some say that mathematicians love when there's no link to reality, we do. Okay, so we want to know why we do stuff, and so now that's how it's nice. So I hope everybody agrees that it's completely realistic, this problem. Speaking about some drunk person finding its way home. I thought when I did MATH.en.JEANS it was this problem, more or less. I didn't think it was realistic. I was like, okay, nice. We've got a drunken mathematician or a cat and a mouse at the time. It's a nice problem, okay, so we can think about it, but there's no real link to reality or to something useful, let's say. And I mean, at least nowadays we've got Google Maps, and even after some years we're able to use it. I mean, perhaps not the Berlin group who yesterday went for 10 minutes in the wrong direction to find the place, but at least after some time, you know you're in the wrong direction, you go to the right direction, and it's fine. Okay. So perhaps that problem is just something teachers invented to get the students motivated, to get some pseudo link with reality and then start. But then yesterday we've got a presentation, and apparently there are like PhD students doing the same thing. So apparently there is something important behind it. And I want to use this problem and show that there is a lot of links to reality, a lot of applications of this, and try to convince you that these simple and weird looking projects or problems can be extremely useful when tackling real life problems. And so let's get to the first example. And it's the finance market. I think that most of you are not too familiar with it, not yet, perhaps later on. But don't worry, there's like, I'm not an expert myself, so it will be a very easy level of understanding. But before we get there, first we need to translate everything that is in the problem, so the drunkard, the street, and everything. We need to translate that into the language of mathematics, the language you've seen in the classes, so numbers, function, graphs, something we can work with. Okay, so how can we do this? We've seen a little bit yesterday with the crab. It's the same idea. So we've got our street, and now we can number the houses like in a usual street. But with the difference that we will do it more intelligently and assign the 0 to the bar, because that's our starting point. And then we will just decide arbitrarily that the numbers on the right will be positive and the numbers on the left of the bar will be negative. And then we will do a trick and flip it on the side, because that will be useful later on. And we'll add a new axis, which will be time, so that we can trace out the steps that the drunkard does and not only see sliding from one point to the next. So the example that we had before is just that he goes right, or in this case up, up again, down, and up again. Okay, so now we're nearly there. So that's already looks like a graph. That's very nice. We just forget about the houses and only worry about the numbers and fuse them together, and we've got our usual graph. Okay. So that's very nice. The thing is that I can do 5 steps. Took me hours to animate this, so I won't do any more, but I wrote a small program to do it for me. We've got time on the x-axis and the street on the y-axis, and we see the drunkard move. Okay. It looks quite different from what we had at the beginning. It looks like a lot more chaotic. Does anybody have seen this sort of graphs, perhaps in the news? Yes? Bourse? Yeah. Exactly. So that looks quite a lot like the stock prices, the stock market prices. So there was the image that we got before, and that's the price of gold. So it looks kind of similar. Okay? And we've made a discovery. Yay! So we can perhaps patent it, but unfortunately, has already been done. Somebody else got the same idea more than 100 years ago. So that's gone. A good-looking guy, French guy, Louis Bachelier, Unfortunately, is forgotten now because the people at the time didn't realize the great ideas he had. But he was the first to use this drunkard's walk to understand the stock market. Okay, so that's the first possible application. And I mean, today it's not like the people don't use just the drunkard's walk to analyze stock markets. They have like more complicated models, but the drunkard's walk still is essential and very important to this theory. And perhaps you have heard of the Black-Scholes model, which got a Nobel Prize in economics, and it's exactly this. More or less, exactly more or less. Okay, so now that's very nice. So the model, the concept is the same, but what about the problem that we had at the beginning? The problem was, will the drunkard come home or not? And let's imagine she lives at number 2000, for argument's sake. Then in the language of finance, this just becomes, will the gold price be larger than 2,000 euros at some point? Okay. And so understanding how the drunkard works on the line is perhaps understanding whether we should buy some gold or not. So are there any questions until now? Okay, perfect. So let's get to the next chapter. Okay, it's not only biology, it's more between biology and physics. And we will complicate a bit the model, okay? So instead of just having a street, we'll go across the Atlantic to Manhattan. And Manhattan is a very special city, and the mathematicians love Manhattan because it's a squared city, okay? So the map is exactly that. And now we place the drunkard. She just left the bar, but now she has 4 possibilities to go home or to take a direction: up, right, down, or left. And she takes equal chances, 25% each, and just goes up. Okay. Forgets where she came from, takes another step, perhaps to the right, again forgets where she came from, another step, and another step. Okay. Now the same problem. We need to translate that into the language of mathematics. Some ideas. Yes.
Like we saw yesterday with the crab's walk in 2D, we could trace a pattern on a planar sheet of paper and like code time with the different colors.
Mm-hmm. Yeah, this was very great with the colors. I don't have that. It's not. I'm not. I don't have a fancy simulation with colors, but that's exactly the idea. So instead of numbering the houses, this time we will number the crossroads and give them points instead of numbers. Or perhaps in a more familiar way, we've got the axis, and then the drunkard can move along the dotted lines. Okay. And so in exactly the same way as we saw yesterday, we don't add time as a dimension, but we just animate it, and then we hope that we can understand the passage of time in this model. Okay. Same question. Has anybody seen similar shapes, perhaps? A bit more difficult. Yes.
Yes, actually, I've worked with a similar problem in the internship. So, for example, this is three dimensions of CO2 particles propagate in a room, for example, are often modelized by such model.
Yeah, exactly. That's one thing, or perhaps more easy for the other. Smoke, for example, is a bit moving like this. I did the second one. It's just the same thing, but we're looking from far away directly instead of zooming, which can be perhaps easier to understand. Yeah, so smoke is one application. I will not speak about smoke. That would be too easy. So I will show you another video. There are pollen particles in water or alcohol or something. One of the few videos on YouTube you find about pollen in the water. Apparently there's not many people interested in seeing those videos. I don't know why. It seems pretty chaotic. It's difficult to understand the motion, so perhaps we'll take another video where I trace the path of one particular pollen particle and compared it to the Drunkard's walk we had before. Okay. On the left, it's the same as before, and on the right, we've got a pollen particle traced out. And I don't know about you, but I think that is pretty similar. At least that, like, it's not the same thing because there's chance involved, but it has the same shape, let's say. So that's the trajectory. And that problem is even older than what I just said. Okay, so in the 1820s, so nearly 200 years ago, there's this first time that biologist describes this movement, and he has no idea why. Do you know why it moves in this weird fashion? Perhaps the older ones. Why shouldn't it just move with the water flow? Yes?
Small molecules that the pollen particles run in directions with the.
Exactly. So we will have many, many little particles around that we can't see, pushing the pollen particles around. But now you have to imagine 200 years ago, they didn't know about things they couldn't see. So they didn't know. So we've got this man, Brown, not very well known, but his name is very well known today, for a reason I will come back to. And he thought perhaps they are alive. Perhaps it's like motion because they're like animals swimming around in the water. And so he did tests and he said, no, it's not alive, but I don't understand this motion. I have no idea why. And the guy on the right, a little bit more known to the wider public, Einstein, 100 years later or 80 years later, he said, okay, imagine there are little molecules around. What would happen? And he found that in this case, the pollen particles would do a drunkard's walk. And that's exactly what we observe. So in some sense, this observation and this connection shows that there are things so small we cannot see it, but we have to take into account to understand nature. Yes? Exactly. So Drunkard's motion is also called Brownian motion for this reason, because mathematicians are super original in naming quantities, and so in what follows I will often mix them together. So sometimes speaking of the Drunkard's motion, sometimes speaking of the Brownian motion, it's the same thing. Okay, and so in this context, perhaps we can change a little bit the question we want to answer and say, how long does it take for the drunkard to go some distance? And this becomes, in the context of particles, perhaps what is the speed of the particles? Okay, so it's with a little grain of salt, because it's difficult to speak in this context about the speed of the particles, but let's just imagine at the speed, and we will be fine until you are like Bac plus 3. Okay. Any question for this part? Yes.
Bon, mais je n'ai pas compris pourquoi il y avait simplement une ligne, dans le sens où dès le début, il a 4 possibilités. Alors il devrait y avoir plein de lignes différentes,
en fait,
parce qu'il y a plein de chemins différents qu'il pourrait prendre.
Oui, si on dessinait tous les chemins possibles, oui, mais ça, on n'y verrait rien. Donc en fait, on va choisir au hasard une des 4 directions. On la dessine, et de nouveau, et de nouveau, et de nouveau. Okay, donc si je faisais la simulation une deuxième fois, ce serait un autre chemin qu'il ferait. Parce que
Au final, on ne peut jamais avoir un résultat qui s'applique pour tout, parce que ça dépend de quel chemin il prend.
Exactement. Et donc maintenant, la question c'est, est-ce qu'on peut quand même donner avoir des informations, avoir des résultats pour déterminer, par exemple, OK, j'en ai plein des particules. Je ne sais pas comment une seule particule fonctionne, mais est-ce que je peux dire quelque chose sur toutes les particules ensemble? Ça, c'est le type de questions qu'on peut poser. Oui.
Est-ce que ça fait longtemps de trouver la particule qui est...
Comment ça?
Parce que s'il y a plusieurs particules différentes et les particules de façon différente.
Oui, donc sur la vidéo d'avant, tu veux dire sur la vidéo de Pollen?
Oui, vous aviez montré un graphique et correspondait à la trajectoire d'une particule. Est-ce que ça a duré longtemps de trouver 47 particules?
Donc, en soi, les mathématiciens, ils simplifient et disent toutes les particules en ce mouvement brownien. Okay. C'est pas vrai, parce que il y a le mouvement de l'eau, et donc, oui, ça m'a pris des heures pour trouver une particule qui donnait une bonne image. Oui. Il y en a plein d'autres qui n'ont pas fonctionné. OK. So that's very well, but that's all problems that are 200 years old or 100 years old. So why are we interested in it if all the problems are solved? Okay. So the next one is, oh shit, wrong one, okay. The next one is about where do we use drunkards now, okay. And so I will speak about my own internship I'm doing with Navier-Stokes at the moment, and I started like a month ago or something. And so we take the same problem as before. We'll take the pollen particles, but this time we'll take multiple pollen particles, okay, and try to understand, can we also understand the water molecules around it and how they interact between each other. So in other words, we've got like big particles for the pollens and a lot of small particles, for example, water molecules, okay. So now, how would you imagine, like, just forget about water right now. How would you imagine the 3 pollen particles to move? Yes.
Juste une remarque historique. On a commencé ce projet à Carnaval. J'étais en train de faire des beignets dans ma friteuse et je regardais comment bougeaient les beignets. Et comme les beignets, ils bougeaient comme le pollen qu'a montré Julian, et que tout ça c'était dans beaucoup de particules d'huile poudrante, ben, je me suis dit qu'il pouvait y avoir une interférence entre le mouvement des uns et les autres. Et effectivement, c'est d'un type relativement semblable à cet exemple historique du pollen et des molécules d'eau développées par Einstein et de même temps.
Exactly. So how would you imagine the pollen particles to move if we just forget about water for a moment? Yes?
They move somewhere in the same direction. So, for example, they all move to the left, upwards, so that all go the same direction.
Okay, why are they all going in the same direction?
I mean, if the water is how gravity has the influence, gravity influence all of them at the same time, so they should all move in the same direction.
Imagine there's no flow of water because you've got a box or something with a bit of water in it and the pollen particles. So there's no flow, gravity goes downwards, so the gravity doesn't play a role here either. Yes?
I would imagine that they don't move.
Don't move at all.
I mean, they move a little bit around a center, but I mean, if I look from 1 meter away, I wouldn't see them.
You wouldn't see them, exactly. But now, now we look through a microscope, and we've seen before that when we look at one particle, it's doing Brownian motion. Yes?
I was just going to ask, are they, so there's no flow in the water?
No flow.
No flow. But they're still in the water?
Yes, so there are a lot of particles jiggling around.
I'm saying they would still move.
Don't move like before, like what we've seen before? Yes. But, okay, so we have to add the collisions perhaps, so they can go on top of each other. Okay. So, again, wrong. Okay, so that's what I did here. We've got 3 pollen particles just moving around, jiggling around, Brownian motion, so they get closer, they get farther apart. They just don't care about what the other particles do except for collisions. Okay? Oh, it's very bad quality up there. Okay, it's much better here. But unfortunately, that is not how it works, because right there we forgot to care about the water. Okay, so we use the water to explain the jiggling around, to have this Brownian motion, but the water does more than just that. Okay, so what we have now is a more realistic simulation. On the left, the same as before, and on the right, a more realistic. If you see a difference, tell me. Yes?
I think like on one side it's on a smaller scale, and on the other side it's on a bigger scale. We see those two. I don't. But one is microscopic and one is macroscopic.
You mean the distance between the particles, or what do you mean?
Yeah.
Yeah. Okay.
Well, on the right, maybe there's like water resistance or something, so that when they move, maybe it's harder to move in the water. So in reality, they move less than you would expect.
Yes?
Maybe an explanation would be that if the water hits two particles in opposite directions, there would be less water particles between the two, and therefore there are more chances that particles outside the tube would hit them back together.
Let's check that hypothesis. And you are exactly right. So between, like when the particles get too close together, what we see is that there's not enough space between, can you see my mouse? Not enough space between the two particles to get water molecules between. And so there's like more pressure from the outside holding the particles together. Okay. And so you can imagine that with tens of thousands of water molecules, it's a bit harder than the initial problem that we had at the beginning with one drunkard. And so that's something that is understood in some cases already, and like similar problems or problems a lot with interactions is at the center of research. So that we have different particles, perhaps different types of particles, but they do things between them, and then we have to understand how they work together and how we get the influence between the particles. So understanding the interaction between different drunkards is understanding interaction between particles or between particles and the environment. And that's something that there's a lot of research done in this area. Yes?
Do you think that this drunkard's work could apply on Navier-Stokes?
Okay, so I will come back to that in a second. Okay. Are there any questions for this section? Okay, great. Okay, then let's get to that. Okay, so now we've got three problems, and we've seen that this drunkard's motion is everywhere. Okay, and there's a second thing I want to say here. Because, as I said, sometimes people think that mathematicians are an isolated group, work on their weird problems, and then sometimes it's useful for other people. It's the other way around. Usually, the inspiration for new problems comes from applications, from physics, from biology, from computer science, from sociology, psychology, everywhere. Then mathematicians develop first more abstract models, try to understand abstract problems, and that's very fruitful for the other sciences. So there's an active interplay between the sciences, always. And it's not like some isolated group not caring about the others. And this drunkard's walk or Brownian motion is so important that there's an entire branch of mathematics solely based on this idea of a Brownian walk, Brownian motion. And there are many questions that are still open. So if you're interested, if you're motivated, go for it. Especially because I have the feeling that there are more and more Fields medals in this domain. First because it developed a lot more. And for your question about the Navier-Stokes equation, so Navier-Stokes is an equation to understand the flow of liquids. And in general, that's a very specific class of equations about functions. Okay, and until now, it was all the theory that could be done was in a perfect environment where there's no noise, no measurement errors, nothing. That's not realistic. Okay, so when physicists work, they've got a lot of errors. They've got perhaps in quantum mechanics really noise behind it, and so this 2014 field medal was about understanding this type of equations with noise. And now it's developing like crazy, this sort of questions. So yes, it goes in the same direction. And last but not least, don't think that alcohol is good for your health just because I used it for illustration purposes. Okay, it was useful for the forgetfulness, but not. Yeah, otherwise it's not. Thank you very much. And are there any questions left that we didn't answer? No? Okay, then I will use the last slide for something else. I have the feeling that that it's not very well known which YouTubers do great stuff on the internet, on mathematics. So I've put a few, so there are many more. I've only put people that did videos in English, so I don't have any French references. 3 Blue, 1 Brown is probably for the older, so première, terminale, and afterwards for students going to university. He does a bit more complicated stuff, but very well designed, super beautiful, and I stole the pies from him. So, yes?
Is it the reason why you chose the little pie?
Yeah, exactly. Yeah. So I stole it from his videos, the design. Okay, Steve Mould, he's not doing things on mathematics. It's more on science in general. So he explains facts that we see every day. For example, understanding, I don't know, how soap drips on the floor or how the boiler works, stuff like that. And he's extremely good at explaining and doing weird stuff. Then Tibis is an Australian teacher doing explaining also a lot on the level of students at schools. So that could be a nice thing. And she just did a wonderful project with the Australian government that's worthwhile watching. The next one is another Australian, a bit crazy. He does stand-up mathematics, where he speaks about mathematics in a funny way, or he tries to. Sometimes he's a bit awkward. And he also does a lot of stuff with Steve Mould together. And then number 5, you probably already know about it. They have great interviews with different researchers presenting their work, and yes. Okay, so I think it's more or less finished. But if you have any questions for my what I did until now, university and stuff, you can also ask questions. If you want to have other YouTubers in other domains, we can speak about it. And yeah, thank you very much.